This lesson deals with supplemental problem 4.5. You can find this problem in the ECE302 ebook in the Chapter 4 Supplemental Problems starting on page 4. We'll look at, in this supplemental problem, an automatic volume control circuit. Using a JFET transistor, so I'd like you to obtain a copy of the ECE302msu N-channel JFET datasheet. As we've seen before, datasheets have a great deal of information in them. Assuming that we're using a typical 2N3819, which is found on page 7-2 of this ECE datasheet, can you deduce from the static DC table what the value of the pinch-off voltage is and the value of IDSS? Then create a SPICE model for this 2N3819 transistor and write a PSPICE file to test your model such that you produce the output characteristic curve shown on page 7-3, center right. Then can you figure out how to have the same y-axis, which is going to go from 0 to 15 milliamps, and the same x-axis, which goes from 0 to 10 volts. Next, I'd like you to write a PSPICE file for the circuit shown below, which is taken from a National Semiconductor Application Note number 32 on page 5. It's called a variable attenuator. For this circuit, I'd like you to put a voltage here of 0 volts and a sine wave for the input of 50 millivolts at 300 hertz. For your PSPICE circuit, I'd like you to plot 3 cycles of your input and output, then measure the gain. If you assume that the JFET is operating in the ohmic region, derive an expression for the gain. Then compare by calculating the percent error the following way. Take the simulated gain minus the derived gain over the derived gain times 100%. Measure the gain in 4 again if you double the input. Repeat all of this for a control voltage V sub C of minus 1.8 volts. We're going to remove the battery that was here and replace it with a capacitor and a resistor and a diode. It's going to become a half-wave rectifier. Write a PSPICE file for this circuit and plot 3 cycles again for an input of a sine wave of 50 millivolts at 300 hertz, and again measure the gain. Next, repeat 7, but now double your input. And lastly, can you explain what's happening in 7 and 8? The first task was to find the datasheet of a ECE2N3819 JFET transistor, and I found a datasheet on this website, dtsheet.com. There's probably several other places you can also find it. Let's take a look at that datasheet. As you can see, it's a little different than the datasheets we looked at previously. Typically, the cover has information about the device. Here we've got a product summary, some of its features, what they claim to be benefits, and then applications. You usually find all of this pretty positive. Then a description of the transistor and what frequencies it's good for, pinout, then absolute ratings, and then what we're interested in is the static characteristics. There's a table that says that's static. Dynamic will be AC response, and we'll look at that later in the course. The pinch-off voltage is listed in this particular datasheet, like our previous ones, as V sub GS off. Here it's giving us a typical value instead of just a max and a min. We're going to use the typical value. Here the actual sign is correct. Pinch-off voltage is minus 3 volts typically. IDSS is actually labeled correctly. In this case, the typical value is 10 milliamps. There's a max and a min range on this, so there's quite a variation from transistor to transistor. And we'll have to worry about this in some of our designs. We found that the pinch-off voltage was minus 3 volts and that IDSS was 10 milliamps. Now we need to know the value of K for our calculations, and that's called beta in SPICE, and that's IDSS over the pinch-off squared. It's 10 milliamps over minus 3 squared, and that's 1.111 milliamps per volt squared. And then the term VTO in SPICE is our pinch-off voltage, and it has a value of minus 3 volts. Take the curve tracer from our class notes, modify it a little bit. Got my transistor, here's my drain gate source. I've got a voltage source across the gate source, and I've got a voltage source across the drain source. I have a title for my SPICE file, and you can have comments. This is what we did in the class notes. My drain source voltage, I'm going to vary, so I'm just going to label it just as here from 2 to 0, but not put a value here. The default value is 0. Same for the gate source voltage, put a battery here, and I'm going to vary the value. Our transistor has to begin with the letter J, and then you can put a letter or number after this, labeling the drain gate source 210, and then I'm going to call this a 2N3819. On the dot model line, use the same name, tell it that's an N-channel JFET, and then give it the parameters that we have talked about so far. There's many more to talk about in the course, but right now VTO is our pinch-off voltage of minus 3, and beta is 1.111 milliamps per volt squared. In SPICE, uppercase m and lowercase m mean the same thing, milli. I'm going to vary the gate source voltage and the drain source voltage. But let's go look at the data sheet first. Go look at the following page. So here's a bunch of numbers in a table, and then usually there's a series of graphs. And one particular graph was called out in the problem was this one here for a off of -3 volts. Plot the drain current versus the drain source voltage. Start out at 0 and then eventually go to -1.8 volts, but we're going in steps of 0.3. I'm going to recreate that in my SPICE file. Gate source voltage, I'm going to vary from 0 to -1.8 in 0.3 volt steps. First one will be 0, and we'll have -0.3, and then so on down the line. I'm also going to vary my drain source voltage so I can get this plot where I've got the drain source voltage on the x-axis and the drain current on the y-axis. I'm going to go from 0 to 10 volts because that's what that picture showed here. 0 to 10 volts. I also will change the scale here, match that, and we'll talk about that shortly. Vary the drain source voltage from 0 to 10 volts. I'm going to put a lot of data points on, so I'm going to do 2,000 data points. So dividing this difference by 2,000, I get 5 millivolts per step. Here's the simulation. It looked quite different than this, and so I was trying to make this size change so that it was pretty much the same ratio of width to length as it was in the data sheet. What I did was I chose in the printing of this to do 2 plots per page with a 2-inch border on all sides. You can also change the scales here if they don't come up this way. This one most likely will come out this way, but you can also change the x-axis and the y-axis scales in the pull-down menus. Next, I need to write a SPICE file for this circuit that we were given in the problem. I have a title, I have a dot end, I have the nodes already numbered for me. Here's 1, 2, 3, 4, and 5. My input's a sine wave from 1 to 0, has an average value of 0, a peak value of 50 millivolts, and a frequency of 300 hertz. I have a 100 ohm resistor between nodes 1 and 2. My transistor is between the drain, gate, and source. So it's going to be 2, 5, and 3. My battery here is between 5 and 0, and I'm going to start out with a value of 0. Got this feedback resistor between nodes 3 and 4 and with a value of 10K. And then I've got an op-amp, which we can model as a voltage-controlled voltage source between nodes 4 and ground, sensing between 0 and 3 with a gain of infinity. But we can't have infinity, so we're going to use 10 to the 8th. Our JFET has a VTO and a beta, as we described before. And now I want to plot 3 cycles. 1 over 300 hertz times 3 is 10 milliseconds. I'm going to take that number and divide it by 200 and get 50 microseconds. We'll start printing at 0, and I'll make the sealing step the same as the print step. Here's my input and output. As you can see, I've got 3 cycles. My input goes from 50 millivolts to -50 millivolts. And then here's my output for a gate source voltage, which is also the controlling voltage of 0 volts. And I have a peak value here of 2.0052 and a minimum value here of -1.9938. The gain is the ratio of the output to the input. In this case, I'll do it peak to peak. There is a phase shift here, so I'm going to put a minus sign out in front. The difference of these two over the difference of the 2 inputs gives me a gain of -39.99. On this op-amp circuit, the gain is equal to minus the feedback resistor divided by the sum of the input resistors, which is 100 ohms, and then I have my JFET operating in the ohmic region with a value of RDS. We have a formula for that in the class notes on page 23 of chapter 4, and it's 1 over 2K, quantity, gate source minus the pinch-off. A is equal to 1.111 milli, and multiply that by 2. Gate source is 0, pinch-off is -3, that gives me 150 ohms. Ratio of 10K over these 2 resistors, which is 250 ohms, is -40. My simulated gain minus my derived gain over my derived gain times 100% is a -25 milli%, basically 0. The reason for this is the model that we're using is identical to what's in SPICE. We'll see later that there's more detailed modeling of some of the transistors, and our equations will be just approximations. But in this case, they're exactly the same. Next, let's increase the amplitude of the input from 50 millivolts to 100 millivolts as a sine wave at 300 hertz. I was just changing one number in that previous SPICE file. Plotted the input, which again is going to go in 3 cycles. Now from 0 to 100 millivolts and then to -100 millivolts. My output's at node 4, and you can see I had the phase inversion of an inverting amplifier, 3 cycles. My control voltage is my gate source voltage, and that's 0 volts. And now my peak values are 4.0222 and -3.9755. We have a phase shift here of 180, so we're going to take care of that here. The difference of these two is the peak-to-peak value, and likewise the difference of these two. And I get now a gain of 39.9885. My calculated gain is still minus 40. My error is slightly different, not much, of my simulated gain minus my derived gain over my derived gain times 100%, and I now get 28.75 millipercent. Slightly different than the last one, but not much. Let's change our gate source voltage from 0 volts to minus 1.8 volts by changing the voltage on the battery, V sub C. Let's go back to our 50 millivolt peak sine wave at 300 hertz. And let's now plot again the gain. And let's also calculate the gain with our formula. The results are on the next page. Here's node voltage 1, which is our input voltage. Output's at node voltage 4. Again, this is for a control voltage or a gate source voltage of minus 1.8. I do have the phase shift of the inverting amplifier. But now my peak is 1.0658, and my minimum is minus 1.0388. And let's go back and calculate the gains now and compare it to the drive gain. Here's our minus sign representing the phase shift. Our peak to peak is the difference of the two peaks over the difference of our two input peaks. And that's now minus 21.046. Our resistance is changed because we've changed the gate source voltage to minus 1.8. We have 375 ohms. 150 ohms when the voltage of the battery was equal to 0, and now with the battery voltage being minus 1.8, we've increased the resistance from 150 to 375. That's in series with a 100 ohm resistor. Our derived gain would be the ratio of the feedback resistor to the input resistor, and that's now minus 21.0526. And then calculate our percentage error with the simulated gain, derived gain, divided by the derived gain times 100%. And that's minus 31.35 millipercent. Again, very, very small, essentially 0. Our next task is to double the input voltage, so we're going to go between 100 millivolts and minus 100 millivolts. And our output's going to likewise increase in magnitude. Now it's 2.1583 volts down to minus 2.0496 for the same gate source voltage. Let's take a look at calculating the gains for this case. Again, have the phase shift, so there's our minus sign. The difference of the max and the min for the output, and likewise for the input, now gives me a ratio of minus 21.0395. Well, the gain is very similar to our previous case. Our derived gain is still the same of minus 21.0526. We can now calculate the percentage error with the simulated gain minus the derived gain over the derived gain times 100%. A little bit of an increase, and what's happening is we're getting a larger signal across the FET, and it's a little bit nonlinear, so we're going to start to see some departure from a perfect behavior. Our last task is to replace the battery by this capacitor resistor diode circuit. We have the same splice file except for this part of it, so we've got a capacitor between nodes 5 and 0 instead of a battery, and that's shown right here as a 1 microfarad capacitor, a resistor between 5 and 0, which is 100K, and then a 1N4001 diode between nodes 5 and 4, shown over here. And then we'll put our model for the 1N4001 diode we had previously in the chapter 2 notes, I sub S of 997 picoamps, and eta equal to 1.67. Simulation results for this on the next page. Let's take a look at those. So here's my input going between plus and minus 50 millivolts. My output is here. Again, I have the phase shift, and I also plotted the voltage across the capacitor, and you can see it charged up and then leveled out. It's leveling out at minus 1 volt. I can calculate the gain, the difference of these two over the difference of these two, multiplied by minus 1 because of the phase shift. And then I ran the simulation again, but this time increasing the input by a factor of 2, so it's 100 millivolts, minus 100 millivolts. And you can see the output has increased. It's now 2.3325 and a minus 2.2136. And the capacitor voltage in steady state is now minus 1.7 volts. We have a transient analysis here and likewise on the top. Let's go back to the previous page and take a look at the results. We're calculating the gain. For the 50 millivolt sine wave, got a phase shift, so here's my minus sign. The difference of the two peaks of the output over the input difference, and I get a gain of minus 30.737. Now I've doubled the input on the same circuit. Again, take the difference of the two peaks for the output and the input, minus sign because of the phase shift, and I get a minus 22.731. I doubled the input, but my gain changed. Our last task is to explain what's going on. Let me scroll back up to the circuit that we added. This is a half-wave rectifier with a smoothing capacitor and a resistive load. As the magnitude of the output increases, the magnitude of the voltage here increases, but it's going to become more and more negative. The more negative this is, the more negative the gate source voltage is, and the higher the resistance of the JFET. As the output starts to increase, we begin to increase the total resistance here, and that makes the gain go down. That's what's happening here. As we were increasing our signal, it was lowering the gain. Ideally, I would like this to be half the gain if I double the input. In other words, if the gain here was minus 30.737 divided by 2, or minus 15.37, I would see no change in the output signal for a doubling of the input. That's called an automatic gain control circuit or a volume control circuit. This one's not perfect, but it's moving in the right direction. And this is supplemental problem 4.5.